Hello everybody. Today our lecture number 5 of design and analysis of an algorithm is how we are going to judge the algorithm, or we can say what are the efficiencies of this growth. What do you mean by of this growth? What are the efficiencies of order of growth? Okay, there are three efficiency classes, or there are three things which we can use in order to judge an algorithm. The first one is the best case of an algorithm, the worst case of an algorithm, and the average case of an algorithm. Okay, say for example, I am giving you a list of elements, say 25, 31, 42, 71, and 105, and I am going to write an algorithm to search a particular element which is in the list. So what I am going to do is I want to search an element in the list, and for that I am going to write an algorithm. And your task is to find at which position that element is in the list. The element which you want to search, okay, is the element which you want to search, we have to find the position of that element. Okay, if we will do this, say for example, if the element which I want to search is 25, let this be k. K is a variable in which I place the element which I want to search in this list, or whose position I want to find out in this list. So if we will see it, if we will take this 25, the kth variable, okay, I will take this element and will compare it with the list. You will keep this in an array. Obviously you will see whether if 25 is equal to 25, then say yes, the element is present in the list, and the element is present at the ith position, whichever position it will be, right? In this list, the element which I want to find is 25, and 25 is present at first in the list. This is the first element in the list. That means I only compared it once. So how many comparisons I did? One comparison. How many comparisons I did? One comparison. I compared the element with the first element of an array, and I got it at first, right? That is called as the best case efficiency of n elements. Okay, so this we can write it like this: the best case efficiency of an algorithm whose input size is n is equal to 1. That means whenever the best case, when you have to perform one comparison, or you have to compare, when you have to perform few comparisons, then we say the best case time efficiency of that algorithm on n input size is equal to 1. So this is the best case efficiency of an algorithm, and it is usually written by this. What is this? Why we write it like this? I will tell you in the next lecture. Okay, so you got it. Whenever you are writing an algorithm, say searching, sorting, whatever, when you have to perform one comparison or few comparisons in order to get the solution of your problem, that is called the best case of a problem. Why we write it as big O of 1? Not because we did only one comparison. No, when we compare things once, or for few times, if 1 2 3 4 5, there are 5 number of elements, obviously uh, uh, I wrote it like 1. If there is 1,000 elements, that means n is equal to 1,000, even 50 comparisons will be equal to 1, will be considered equal to 1, because that, in comparison to 50, that is very small. You didn't perform so much of comparisons in order to find the result. That is the reason why. And big O of 1, whenever we write it like this, it is called as the constant time. Okay, so that is what we call as the best case for any algorithm, for any problem. When you do not have to perform lots of comparisons, the that is called as the best case efficiency. That means you got the solution at first or instantly. Okay, hope you got it. Okay, now the second case is the worst case. Say I am taking the same element. Now the element which I want to search, okay, is, say for example, 105. So let k is equal to 105, and the number of elements are 31, 42, 71 and 5. Okay, now I have to take this element and I have to compare it with this. So how many comparisons? One comparison. I have to take the same element and compare it with this. Because I didn't find the element, I have to take this. I have to check whether the element is present in the list. If it is, then find the position. So I have to take this and compare it with this. I have to take the element and compare it with this. So here I did one comparison. In order to find the element, I did two comparisons, three comparisons, four comparisons, and at the fifth comparison I got the element. Right? In this case, n is equal to 5. Right? So I can say, and I am saying, in worst case, the element which you want to search is either present at the end of the list or the element is not present at all. Okay, now in this case I took the first one, that is say for example the element which you want to search is present in the list and the element is present at the end of the list. So what will be the worst case? So worst case of such algorithm on n input size will be equal to n, and we can write it like this, will be equal to n. Why? Because you have to perform n number of comparisons in order to get the element. Didn't we performed 5 comparisons, 1 2 3 4 5, and in this case our input size was equal to 5. So I didn't mention the constant, I mentioned the variable, because it depends. Your in this example your input size is 5, but it can vary, right? You can take it as n. So the worst case time complexity of this particular list in order to search the element is big O of n when the element is present in the list, right? Okay. Now if I am having the same set of elements 25, 31, 42, 71 and 105, and as a user I want to search the element 10, right? So again this 10 will be compared to this, then to this, then to this, then to this, then to this. Then a message will be displayed that the element is not present in the list. But still, in order to search the element, in order to see whether this particular element is present in the list or not, we performed n comparisons. So the worst case time complexity in this case is again equal to big O of n. So this is when element is not present in the list. Okay, so this is the worst case. Now the last one is our average case. In average case, what happens is there are again two cases. There is a probability that the element is present in the list and it will be present somewhere in between the list, maybe in the middle, maybe after a middle position, or like that, right? In the average, the element is not present in the first, because that would be the best case. The element is not present at the end, because that would be the worst case, but the element is somewhere in between the list. Okay, but in average case there is a probability that the element is present, or maybe the element is not present in the list. So what we have to do? So we will consider that the element is found somewhere in the middle of the list. Okay, somewhere in the middle of the list. and the probability of successful search is, say we represent that with P, where this P lies between 0 to 1. That means 1 means if the element is present or the element is not present. Okay, fine. And the probability of unsuccessful search, that means when the element is not present in the list, will be represented with P minus 1. Okay, like this. Now consider that element which we are searching is found at position I in the given list, whichever list it would be. If the element is present in the list and the element is present at what position? At the ith position, then the probability is P by n. Common sense, right? It will be P by n. So we can say the average case time complexity of any algorithm, in this case, okay, I took the example of linear search, you can easily get that, will be equal to 1 into P by n. There is a probability that the element is present at the first place, plus there is a probability that the element is present at the second place, and like that. There is a probability that the element is present at the ith place. Because we are generalizing it with n, so we do not know how many elements we are having, so at the ith place, plus there is a probability that the element is not present in the list at all. The first half up to this is the probability for successful search, and this term will give us the average case for the unsuccessful search. Clearly from this we know that P by n is common everywhere, so we can put that out. P by n, then there is 1 plus 2 plus 3 plus I plus up to n, isn't it, plus the unsuccessful term, right? Okay, you clearly see that this is the summation of n natural numbers. So by substituting the formula of first n natural numbers, that is the reason why I told you before, you must know the programming language, you must understand the data structures, and for all these formulas you must have some discrete mathematics background. So you know that the formula for that is n into n minus 1 divided by 2 plus unsuccessful search term. This n and this n will get cancelled out, so we are left with P into n. Okay, this is n into n plus 1 divided by 2, n plus 1 divided by 2 plus n into 1 minus P. This is the first term and this is the second term. Now we will take two cases. Take two cases for in order to find the average case of any algorithm. The first case for this particular example will be, say for example the element which we want to search is present in the list. That means your probability will be equal to 1, which represents that the element is in the list. Now where is that element? That we have to see. Now substitute this P equal to 1 in the first term of the formula, in this, plus n into 1 minus p in both the terms actually. So p will be 1 into 1 plus 1 divided by 2 plus n into 1 minus 1. This will get cancelled out. This is 0. The whole term will be equal to 0, right? So there we will left with n plus 1 divided by 2. So therefore we can say the average case time complexity of this example of the linear search is equal to big O of n plus 1 divided by 2. But always remember, whenever we talk about complexities or the cases, consider we don't take constants into consideration, so we can simply write it as big O of n. Okay, this was the first case when the element is present in the list. The second case would be, what if the element is not present in the list and you want to find its average case, right? So that means for unsuccessful search, so we have to take p is equal to 0, right, and substitute in the same formula. 0 into n plus 1 divided by 2 plus n into 1 minus 0. So this whole term will be equal to 0, and here we can get the n. So average, this term will be 0 and this will be obviously 1, n into 1 is n is equal to big O of n. And we can say that when the element is not present in the list and you have to find the average case, that is basically nothing but the worst case. This is when p is equal to 0. Okay, so this is how we can judge our algorithms. We judge our algorithms, or we find the efficiencies of the order of growth by checking the three cases of the problem or of algorithm. That is the best case of that particular algorithm, or the worst case, and of the average case. If there is any question you want to ask, do ask. Thank you so much.